So let's get started. Thanks everyone for being here for my spontaneous next virtual class. So this one I titled A Chaotic Time, and it really is, I mean, all of this and any of this stuff that I'm doing. Why am I doing this? I like to kind of start with why, what's the purpose, or at least what's the purpose of me digging into all this stuff and trying to share it. Well, for one, all of this is really just my own independent research. None of this is funded formal research. This is literally all my own mental rabbit holes and all of my own curiosity. So that's why I'm doing any of this. And everything that I'm talking about today is literally just me sharing all of my most recent interesting, fun rabbit holes and thoughts and these things that I think about all the time. So that's kind of why I'm doing it. And my intention is for today specifically to my intention is for after this, for you to have leave with a different perception of your surroundings. I feel like there's a floating orb that I just saw in the camera. I would say one of my intentions is to alter your perception of the world around you. Let's go with that for this one. So a through line here is how do we discover something that isn't immediately visible is kind of a through line thesis statement of this talk. So an overview really ended up getting a lot into the definition of time itself. So, kind of how I've structured this is starting off by how we define time historically, scientifically, the search for a timekeeper, for rhythm. Next, a little bit about the psychology of what's hidden, what we can see, what we can't see, and a lot about human perception. And then patterns, the difference between randomness and chaos and order and deviations from the norm. And then getting into chaos theory and really fractals and how we can think about this to apply it to space-time hidden regions. So that's our overall layout here. All right, so I got the chat open and cool. All right, so I'm starting with, and really a lot of this, okay, this all starts with time being stranger than we think. As we know, or if you're here, you probably are interested in time, or you're just my relative and you're flattering me. Hey, cousins. So no, I'm kidding. So time is of course stranger than we think. So what I really want to start off with is, and what the whole first part of this was inspired by, was this thought about clocks drifting. And why, first off, why that happens in the first place, and then really to get more meta with it, what it means and what it's telling us about the nature of time, right? So we really have to go back to, if we're going to talk about clocks drifting and this idea of what is time, you kind of have to go back to what is time? How did we ever define the second, any units of measurement? And let's kind of really just, um, peel it all back and go to the basics. Where do we start? How do we start defining time? So, and yeah, and but more so, what I think is the most interesting part of it is what was the intention, or what was the inspiration? The inspiration in this search for timekeeping, for accuracy. So, how did it all start? Um, and I talk about this in my astronomy classes all the time, the history of ancient astronomy and everything. But of course, astronomy is the most consistent timekeeper initially, or this is how it was treated in history, meaning what the most consistent rhythm or understanding, yeah, of cycles that we know is, of course, the day, the length of a day, the sunrise. What's the most consistent thing that we really see is nature. But I mean, this talk is about, is nature rhythmic, or is it out of sync? That's what all of this is about. But so we see this repetition of the day, right? So the Babylonians were actually the ones that were the first ones to define the second. By the way, a lot of this stuff that is at the beginning part of this, I honestly hadn't researched this until I was putting together this talk. So I don't even know how that skipped by me, but I learned like all of this really recently, and it's exciting to me. So the Babylonians, they really liked the number 60, and Why? Because it was the smallest number, one of the smallest numbers that was divisible by the most numbers. So you can see it, the number 60 is evenly divisible by 1 through 6. After that, it's not divisible anymore. But by 6 integers, it's divisible by. So they really like the number 60, and then they use that as the inspiration to subdivide the day, right? So then that's how they came up with the 24-hour day and the minutes and seconds, but really it was subdivisions based on 60. So they decided the length. They were technically the first ones to decide the length of a second. And then the pink here is just a bonus thought, right? There's my thoughts, and then there's bonus thoughts on top of all the thoughts that already feel like bonus thoughts. But that one is just that when I was writing this, I was thinking, well, because I'm always thinking about infinitesimally small units of anything, like infinitesimally small units of matter, smaller than the Planck length. So then it made me think of, and I mean, yeah, it just made me think of the fact that technically there are infinitesimally small indivisible units of time. And I guess I had never thought about that before. I don't think, until this moment. So it all comes back to, though, the rotation of the Earth, right? This is our core rhythm that we're relying on. So then when we set out to say what makes a clock, right? So then we defined a second. So then now in the course of history, we're trying to define time and do timekeeping and make time real and define a consistent clock. What are they looking for? They're looking for something that repeats. And really, at its core, it's something that can be counted. So historically and in our societal sense, we're treating it as, well, for one, we're looking for consistent rhythm, but what we're really doing is we're counting. And so the Babylonians decided that 1 second was that length. And then we set out to say, okay, what object in nature has the most consistent pattern that we can use to count, and then use that counting to define a second. And then that is how we start getting on the trajectory of like what an atomic clock is, and all this stuff. So really, our search for timekeeping was the search for steady rhythms, something that repeats steadily that we can count. So then I was researching about gears and a clock. This was another thing that I don't know, I always think about, but I guess I had never really researched it. So then I was like, wait a minute, what do gears and a clock do? And so I was looking at those because I know, you could think of them as turning, but I had never really thought of it as these equal subdivisions and how the teeth on the gears, and I mean, everyone has their different like brain spaces that they're coming from, and I'm an astrophysicist, but I'm very much not an engineer, so I don't really think about these like mechanical things that much. So then when I was thinking about that, I was like, whoa, okay, so it's subdividing ratios, right? So everything, it all comes down to taking some whole and subdividing it into what we're forcing on even intervals. So that's how clock gears work, and that's why clocks are trying to attempt some consistency there. But what happens when we realize, so then here in the story, we realize that what we were going back to, what we were considering our most reliable baseline timekeeper, the rotation of the Earth, is actually not even reliable in itself. And this is where everything, I think, gets really wonky, or this is what I think is like the base of everything. Earth's rotation, and some of you might know this, but our rotation rate, I mean, this is why we have leap seconds and days and stuff. Our rotation rate is not constant, and it's also not even trending in a certain direction. I think it's sometimes speeding up, sometimes slowing down. If anyone in the chat knows more about any details of that, feel free to chime in. I know we got plenty of astronomers in here. But Earth's rotation rate is affected. Why? Because of gravity from the moon and because its mass distribution is constantly changing. So this just it's pointing us towards or making us more aware of, okay, well, nature and astronomy, the thing that we're relying on here for some consistent rhythm here, is not reliable either, or it's chaotic. I haven't really don't need to jump to that term or definition yet, but it's out of sync, right? And it's because of natural fluctuations, I would say. And so the moon is tugging on the earth, so there's a gravitational pull there. And then also the mass distribution of the earth is changing because earth is not just a rigid body. There's liquids, there's tides, there's ice caps melting and all these things. So So we're not even syncing. And so, yeah, we're not syncing our definition of a second to something that's consistent. We're aware of this, and this is why, this is why leap time exists, but it just points to this weird tension, right? This is how we're defining time. So after this, so then our pursuit for defining the second, right? So yes, working within that, defining the second, a little bit just briefly through history. I learned this too, by the way. I didn't know any of this. I was like, whoa, cool, water clocks, candle clocks. Who knew? Who knew? Anybody else know that they used to keep time with candles? I would love to know. Anybody else know that? So water clocks, candle clocks, and what's the intention with all of this is measuring a consistent, with the water is measuring a consistent drip. We're so desperately trying to find some sense of consistency for what the main reason here, that's part of the story we're at now, is defining some kind of counting system that we can put within the length of a second, really, is kind of what we're talking about. So so we did water, candles, that's giving a little archaic. So let's get a little bit better than that. So then they went to so th then they said pendulums. They said, "Oh, pendulums are rhythmic. Pendulums do this. Let's use pendulums and let's see how pendulums can let's count pendulums." And that was good until it wasn't, because pendulums are imperfect too. Because guess what? They're subject to gravity, air resistance. They are systems that can still lose energy. So pendulums are also oh, David knew about candle clocks. Uh yeah. Oh, interesting. Primitive alarm system. So anyway, so pendulums imperfect as well. So then we go to the quartz crystal clock, which this is fascinating too. Um, how crystals are used to time keep. So again, we're just in a pursuit of something that has a perfect rhythm or close to perfect rhythm. So then I learned all about crystals and how crystals time keep. And there's a term called piezoelectric. I don't know how to pronounce it. Maybe that's right. That is a property of crystals where so they do this thing in a crystal clock where they if you apply an electric field to it, it basically physically moves. So crystals will physically respond to changes in electric fields. And then from that, when we put them into a circuit and everything, what we do there is we can count the amount of vibrations and then use that to define a second. So this is, and these are more widespread now. So these kinds of clocks are in our phone. I think they're in a lot more things, maybe watches. I mean, I didn't do my research to cover the bases of every single type of clock and every single and how every single type of clock gear works. But very interesting. I also found something else that's going to send me down another rabbit hole later about this whole thing with the quartz crystals, and something about the reason it has that property has to do with the number three or some asymmetry. And I was like, oh my God, I don't have time to look into that right now. All right, that's a side note. So crystals keep time that way. But uh, there's there's not perfect accuracy there too. So the crystal clock, sorry, just to jump back for a second. Um, so it's a lot more, I would say it's more accurate than a pendulum, but still these crystals can behave differently under different temperature conditions. So temperature sensitivities can change vibration speeds. So then we get to the cesium atom, which is the current definition of the atomic clock. So this is the real atomic clock if you've ever heard of it. And this is, I would say this is the most like up-to-date version of our timekeeping right now. So the physics of this here, this gets a little physicsy here. So cesium, its atomic number is 55 on the periodic table. So there's a specific transition here. There's a specific hyperfine transition. The transition in physics that this is referring to, this is not an electron jumping from one energy level to another energy level. This type of transition has to do more with magnetic alignment and so it's essentially an energy transition that corresponds to an energetic alignment or misalignment between the magnetic field of the nuclear region and the magnetic field of the electrons. So there's a very specific transition. The details of how which is basically reliable and consistent. So what we do is they shine. I don't need to get too much into the details of this, but what they do is they shine a not shine. They like beam a microwave. microwave wavelength at the cesium, and then once they get to the exact right frequency that corresponds to that energy transition, then they're basically counting the oscillations of that frequency. So I looked into this and why every single atom cannot be used as for timekeeping, because there is a lot of precision with energy levels and energy transitions in physics and in nature. So it's not that cesium is the only atom that exhibits some kind of consistency with its energy um, with its energy range in that transition. It's more so that it was one of the first that was found that is easier to measure. So we're basically constantly, what we did was we defined a number of periods um, of this kind of microwave radiation that corresponds to this cesium transition. And we said 1 second equals this many vibrations. And this is currently used as the atomic clock. And what we do is we are constantly checking back in. We have defined this and we are constantly checking back in with this cesium atom. And that's what an atomic clock is. That atomic clocks like constantly check in with this to continue to sync the number of vibrations equal to our understanding of 1 second. All right, so that's the cesium atom. So then, where does all of this leave us? We must revisit general relativity and time dilation. So now where we're at is we have our definition of 1 second, and we're saying 1 second is this many vibrations, right? And we have really tried to hone in on a solid rhythm to keep our definition of 1 second consistent. And so then I looked into how does this fit into time dilation and Einstein's general relativity, where time dilation says that time speeds up or slows down in different gravitational fields. And this was honestly something that always, I mean, I learned about time dilation initially in college, and I just remember always thinking what they would say in class is time is clocks tick slower in stronger gravitational fields. And I always used to be like, what do you mean? Isn't the clock just like a battery? Don't we decide the interval of a second? And I've always kind of been like, what do you mean clock? I thought clocks we make. And honestly, I was kind of surprised to learn this information. I was kind of surprised it hadn't really made its way to my brain until now. But you know what? That's okay, because it just goes to show that sometimes you're too busy learning other things to learn that one little thing that you didn't make it into your brain. So cesium, this vibration, this atomic clock also is consistently slowed down and sped up in gravitational fields. So this is supported by Einstein's relativity theories of slowed down time and sped up time are consistent with the atomic clock, meaning that in a stronger gravitational field, the atomic clock, a certain amount of vibrations, would translate to a longer second. So everything kind of consistently changes, which is wild to me, actually, wildly consistent. And I mean, that's so, all right, so back to the story here. We're trying to find some consistent rhythm, right? But we're seeing all of these deviations. So cesium, by the way, is still is a consistent kind of rhythm, but it modifies with nature and with space-time in the presence of different gravitational fields. So it still modifies. So it's still even our most consistent, right? So this, I mean, and this all just points back to the malleability of time. Even our most consistent timekeeper, I mean, it follows this fluctuations, these deviations from time stretching, from time slowing down and speeding up and everything. So it kind of just it's all pointing to this irregularity that's sitting at the bottom of everything, right? We're desperately trying to fix things into some obvious or a clear rhythm when or a constant interval, because that's really what it comes down to. It really kind of comes down to a constant interval. And everything else is pointing to, and nature, the Earth's lack of consistent rotation day, the natural variations in the gravitational system of the Earth, Moon, and Sun, the solar system, just the natural variations of existence and everything, the different gravitational fields, air resistance, like that's why pendulums aren't perfect. Everything is pointing to nothing can really be put forced into constant intervals. Um, why are we doing that? So it kind for one, it kind of begs the question, why are we constantly imposing a constant interval when nature is telling, well, when everything is pointing to drifts and asymmetry and all this kind of weirdness, right? And all this drift. Um, and so it really just, oh, sorry. It just begs the question, well, for one, okay, it's for sort of good reason that we're forcing us, because if everything, it really asks the question, or makes you think, okay, well, what would happen if we just let all these clocks drift? If we just let everything drift? And even digital clocks drift. Think back, think to your car clock. Have you ever seen your car clock drift a bit over time? It just by like 1 minute, 2 minutes, just after a period of time, and I just think it's I just think it's very interesting that that happens. And so the reason though that we try to do this, right, of course, is because I think we would soon realize that once things how would we calculate the propagation of the drift? All of a sudden, we would have a very hard time deciding on a universal now, right? If that drift would propagate really fast and we would not be able to decide, we would not know what is now. And yeah, so that's just what I was thinking. Like, what would happen if we stopped? Like, if we let the drift go? I don't know. Things would get weird. Um, so all this to say, though, the drift is the clue. This is what I'm saying. This is my thoughts. My fun ideas are that the drift is the clue that time is not fixed intervals, or there's something more to the story where there's that deviation might be pointing more towards something that doesn't need to be fixed. Why do we think that deviation needs to be fixed? Why are we forcing it back? What happens, or what would happen if we accepted it as truth? Um, but one thing we have to talk about when we're talking about rhythms and everything, before we move on to perception, you kind of have to talk about. So I was just saying we're trying to find synchronized rhythms, right? We're trying to find something synchronized to create an even time because we're trying to anchor ourselves to a reality. We're trying to anchor ourselves to reality. And but we can't ignore the fact that rhythms also do exist, and that perfect rhythms do exist, and they have a meaning to us. They have a significance to us, right? Because so the universe still does contain beauty in rhythms and in synchronization. Systems sometimes still do want to synchronize, right? Um, so why do these rhythms still keep appearing and having significance in a universe that's constantly drifting? Honestly, I don't really know. When I was putting this together, I was kind of like, oh, I need to think of an answer for this. And I realized I don't think I have an answer. I say we just discuss it for a moment. Where are the other places that rhythms appear, right? Rhythm is, and my interpretation of rhythm is regulatory. For one, the reason we search for rhythm is to create a reason to anchor us to reality. So, right, we're trying to anchor ourselves to reality through rhythm. And but if anything, it's regulatory. The first example that I think of is breath work. I do Kundalini yoga, which does a lot of breath work, and a lot of times we'll do like rhythmic breath work. And I would say the purpose of that is to regulate you and to really kind of because there's something about being on a rhythm that makes you feel safe. There's kind of like there's kind of like a safety there. And see if you can. You can mute yourself. Um, so okay, sorry. So there's like a safety there, right? And there's music. We can't ignore that music has rhythms. And there's something about those rhythms that elicit a response in us. There's our heartbeats. There's the whole biological side of it. The fact that we obviously contain the fact that think that there's an abnormality when our hearts get out of rhythm and stuff like that. Listen, I'm no biologist, but there's significance there. And then there's also rhythm as emotional and poetry. So then it makes me think about poetry, but more so specifically how poetry uses, it's more so like that poetry uses the absence of rhythm, right? Or not the absence of rhythm. The first thing that came to my mind, and listen, I don't really read any poetry ever at all, but the first thing that came to my mind was how does poetry use like change of rhythm to elicit emotion, right? To elicit suspense. So, I mean, I don't know. I kind of tried to have something more profound to say. Sarah, can you mute yourself?
Oh, honey, okay, I thought I was.
Sorry.
Sorry, wait.
Hold
Sorry.
hold
Shush,
on.
I
No.
won't talk.
Oh,
I gotta find a way to
there was
mute.
a part that I was able to mute everyone,
Thank
but
goodness.
then
Okay,
I don't know where it is. Okay, that's fine.
I won't talk until I find the button. Sorry. Go.
Okay. Yeah, okay. So, um, now moving on, sorry. So we were at rhythm elicits some kind of response, right? There's both perfect rhythms in nature, in our bodies, in our experience. There's perfect rhythm, and there's also this deviation from the rhythm. So I guess I kind of just think it's interesting and beautiful that both exist, and it's almost like we are, and it's like they're both belonging to their own system. It's probably like the rhythms are meaningful in themselves, and then the deviations from the rhythm are also meaningful. That's kind of just the way that I'm thinking about it, but I don't know, it's something, I think it's something interesting to ponder, I would say. So all of this kind of to me signals that we're missing something. Because there's some kind of chaotic underlying system. To me, this makes me think, go back to the astronomy of it all, go back to the Earth Moon system, the rotation, the revolution. To me, it says that there's something more chaotic or more abnormal than our minds would like it to be that's going on, that we keep on trying to force a rhythm to. So to me, that says that something is hidden. So now I'm sort of switching gears here to psychology and your mental perception, and how to think about how we discover things that are hidden. Because I'm very obsessed with, in my space-time research, understanding hidden regions or dimensional planes of space-time. Well, things that we call hidden, but that just haven't been perceived yet. So this is a thought experiment, all right? So let's say that we are made up of many chaotic threads, that we are made up of these kind of fibers. I mean, some would say that we probably are. So let's say we're made up of these kind of conscious, sentient threads. If everything else, right? So if everything else around us was made up of these threads as well, or was made up of something else with structure, but we can't immediately point to it. We can't immediately say it's right there. But let's just say if it was made of structure, if it was made of something, how would you see it? Right? How would you see it? Clearly just looking isn't enough because you're not seeing it. So you would see it by interacting with it. You would have to interact with it to see if there is an elicited response, or for you to, or it's kind of like one of those things where, oh, this is just the example that came to mind. I guess I'll say it since it came to mind. It was meant to be said. Like, yeah, if you're looking for your friend in a dark room or something, or out in a field, right? You can't just like see it, but if they see them, but if they say something or if they shout, then all of a sudden there's like some signal or some interaction, right? So there's kind of, through interacting with it is really the moral of the story there. So this phrase, the other side of time, I kind of just felt called to put it on this slide, and with this concept here, um it's been coming to me for a while. The other side of time, meaning, I guess I could also point to this as like the other side of a black hole, the liminal space, all of this stuff. But I guess, what's coming to mind right now is, where's the response? Where's the response coming from? So if you're interacting with some medium to observe the response, where's the response coming from? The other side of time. But what do I really mean by interacting with this? Um, I guess, kind of playing with it, really playing with it. And this is sort of because playing with it because how else are you supposed to know? How else are you supposed to know if you don't F around and find out? You know what I mean? Because clearly the ethers, space, clearly there's more. There's more to what's here. So when we can and then the magnetic fields photo up here, this is magnetic, this is metal shavings in the presence of a magnetic field, and this is always the best example for these kinds of situations of these kind of hidden fields is the metal shavings reveal the pattern of the magnetic field. But we wouldn't know that it's there if it weren't for the fact that it's the magnetic field is creating an effect on the metals. So I would say this is sort of about playing with the universal intelligence and playing with interacting with what's around you and playing with your perception. So this kind of what this all made me think about was and I'm coming back around at the end of this to latent empty space, but what this all really made me think about was I've been playing with the word latent lately, because where I've been using latent as a catch-all for like hidden, hiding potential, unlocked potential, because I've been thinking about that because I've been wondering where there are other planes of existence, other regions of space-time that we don't know about. And I've thought, well, they might be an empty space, but they're latent. They haven't revealed themselves yet. So then I was thinking, what does latent actually mean, though? And what does it mean for empty space to be latent? Does when we call something latent, that's an expectation. That's a mental expectation of there being nothing there. Maybe we're expecting some potential, but it's an expectation that there's really nothing there, right? But there's potential for there to be something there, is what makes me think of it. There's multiple definitions for latent. But is it more so that it's just nothing has been, that we're expecting there to be nothing there and that nothing has been attended to or nothing has been observed yet there? So then I looked up the formal physics definition of latent when I was putting this together, and it made me excited because it made me think of other things. But so latent heat, and in physics it's technically latent. The word latent heat is a type of heat in physics, and it refers to a transition, a phase transition where the temperature doesn't change. So it's considered latent because, or it's considered hidden and latent because it doesn't change temperature. So in a way it's almost imperceivable to thermometers. And I was like, that's so cool because that just makes me think of a lot more things. And also, I've been working with the idea of phase transition to think about these regions of sort of empty space and what else they could be, or maybe already are, just haven't been perceived yet. So all of this to say that, empty space, is it really empty? Is there potential in it? How does our observation of it, right? So if space is made of something and we don't know, how can we play with our observation of it? And how can we even think of what the role of our observation in any of it? All right, so this is some cool thoughts that I had over the last few days, which I was excited about to share. So this is about how reality is big, or okay, what is reality? The universe, the things around us, there's a lot around us, right? Maybe if any of it's real. And most of it never makes it into your awareness, actually. Most of it never makes it into your awareness. And so this is about how we filter what we see and what that means and why it's significant and why we should care about the fact that our minds filter out a lot of things. Okay, so this is just some fun thought experiments because this came up around the house lately for me. Okay, for blind spots, the two separate topics here. Have you ever noticed blind spots in your reality? And what I mean by this is the best example I can give. I'm thinking in my house right now, there's two spots, one in our backyard and one inside, where I swear, and on the backyard one, it's kind of like a raised little patio region, and then in our living room, it's just like an extra little sitting room or whatever. I swear, both of these spots, every single time I pass them, if someone is sitting in that spot all the time, I never see them. It's just like always. it's always creates a blind spot in just this one region, can walk by. And I've just noticed this for years in these specific spots, like just these areas, and they're right there. I'm not even saying that they're darker, that they're kind of like around the corner. I'm just saying like regions of my living space that I've noticed over the years. Sometimes when there's someone there, I just can't see them, or it feels like a blind spot. And so I was curious. I posed that question to you. I posed that question to you guys in here to think about. Think about that. Is there anything that you've noticed that you're like, yeah, for some reason it's like your mind just skips over that region. And okay, well, for one, I just think that well, for one, that says a lot about, it says a lot about what we see, about the fact that regions can be right there, but maybe for some reason, some areas are more susceptible to just like missing our attention or our meaning. And so that was one thing that I thought about. And I don't know, maybe the second one is sure. Maybe it's like maybe those are like little energy vortexes or portals, or I don't know. That's totally, I'm just making that up. But then the other thing too, another version of this. So that's like blind spots in your reality. Another version of this that I was thinking about the last few days is when some place appears to you, or when you, especially if you've like lived somewhere for years, and all of a sudden, you're driving down the street, and all of a sudden you're like, was that shop, was that always there? Or like that one thing, that sign, was that sign always there? And you go back and you're like, I can't believe that was, you're like, I can't believe that was always there. And it just makes you think, well, it makes me think, was that, how can you consider that thing to ever have actually been a part of your constructed reality for the last some odd years that you've been going past it? And then just another example that I'm thinking of too is not even necessarily like, has that always been there? But so in my hometown, I don't know, there's this restaurant that's like on a corner, and it's always been there, and we kind of just never went to it. We never go. So for years and years and years, I feel like I never really like looked at it. I feel like, and I go to that shopping center all the time, and I swear for years I never put my conscious attention on that place because we just never went there. And so I just feel like I skipped over it in my reality. And I don't know, I just think there's so many cool examples of that, and it just makes you it makes you realize how much you filter out, and it makes you think, what's a real part of your reality. Okay, now this one is an idea I'm really excited to share. So this is so sort of I don't know, a download or realization, if you will. And this is about also still sticking with the theme of things that are there that you maybe didn't realize, or things that could be hiding in plain sight. So this was inspired by me seeing a speck of glitter. Well, for one, I love glitter and sparkles. That's just my essence. That's unrelated. I guess I just felt like saying that. So I saw like a flash of glitter out of the corner of my eye once, and I was like sitting on this balcony, and I saw like the little explosion of the not explosion. I make it sound really dramatic. I saw like a little glitter flash or whatever. And instantly I was just like, this whole vision came to my mind. And I was like, oh my God, I just had this realization. And the thought was about how, so then I saw this visual of like this little fleck of glitter floating past. And what's glitter? It's a flat little piece. I have a picture of it right here. It's a flat little piece of plastic, right? And some are bigger than others. So I had this visual of like a glitter fleck floating around, and then it comes through, but you can't even see it because it's so tiny. But guess what creates the conditions for you to see it are very specific, like geometry orientation. And it also, not only that, but this tiny little thing from what? From the conditions being just right. From the conditions being just right. This tiny little thing that you probably wouldn't have seen otherwise creates a whole dispersion of light out of nowhere. And so really what that made me think of is the idea of, yeah, of things that might contain a lot, they might contain a lot of potential, or not even potential, they might just contain a lot, but we're not in the right conditions or orientation to see them. And but the real question is, what does that really mean deeper in a deeper way? Because I'm not talking about, oh, that galaxy is too tilted to the side, we can't see it. Clearly, we're getting a little bit like deeper than that because we're not in that territory. We're not talking about like, oh, this thing is here, I can't see it. So it's kind of, I mean, I don't know, maybe it is as simple as that. I don't know. That's what I'm trying to figure out. So I really loved that idea, and maybe you do, but if you don't, it doesn't matter because I love it. All right. So this idea, yeah, glitter, this hidden explosions or like hidden world, hidden a lot of things in very specific unexpected orientations. All right. So then speaking of right the observer effect, or this role of the importance of our observation in all of this. I kind of just wanted to talk about the observer effect and what it actually means in the classic, back to the classic quantum mechanics, or the classic observer effect, if you've heard of it. So what the observer effect really is that it I mean, it is actually a quantum mechanical definition because it has to do with probability and the fact that there's no localized position yeah, there's no localized position or momentum for an object until it's observed. Because before it's observed, it exists only as a wave function. So it exists as a probability. Before it's observed, it exists as a set of probabilities. Once it's observed, it exists in its precision. Why? Because you looking at it, because for something to be observed, it is a photon, an energy packet of light, going from that object to your eyes. So the reason the observer effect is a thing is because as soon as you look at it, you force it into a position by creating that interaction with the photon and your eyes. So that's what the observer effect is. It it forces it. I mean, it's really because your eyes have to receive light and then they're receiving it from a localized position. Where before, everything is so non-pin downable that it just exists as a set of probabilities. So it's going from probabilities to defined. And I think there was something recently in the news about Nobel Prize or something about local realism, and things don't have a position if you're things technically do not have a position until you are looking at them. And it begs the question, does something exist if you're not looking at it? I don't know. That's a very deep philosophical question, but it is sort of what I'm talking about in here. So, but speaking of that, we have to talk about the human mind. Um the human mind and perception and how we categorize things. So we have we see things, or we assign meaning to things, right? Maybe not right. Maybe that's not obvious. Technically, everything is neutral and our mind assigns meaning to things. That's kind of technically how it is, because how can anything objectively have a meaning? I don't know, we're getting very existential here. So, but our minds need to categorize things. So there's a difference between something that's not seen and something that's not categorized. Is there? I think there is. Because if our mind doesn't know where to sort something, that automatically makes that information more likely to be filtered or to be missed. And it's very proven, and there's a lot, I think there's really a lot of stuff and a lot of these psychology experiments that show people do not see the same things. You can literally have two things. Actually, I just talked about this with my mom this morning. Um, you could oh yeah, because she was saying about something about eyewitnesses in crimes and stuff, something about eyewitnesses and how people literally don't see the same thing. You can have you can have two of the exact same thing happening and people can see different things. So you kind of have to think about the difference between seen and observed versus categorized. So then that, hold on, wait, was there anything else I wanted to say? Yeah. So what's latent? What's latent versus what's just uncategorized? So then that really makes me think, can perception itself, right? So now we're kind of saying perception itself is more of it's more of a mode that can be accessed and tweaked and modified as opposed to ultimate truth, right? So can perception itself be in or out of phase in a way with reality? So, kind of, I'm talking a little bit more about perception, but one thing I really just want to say, really just want to like bring this all to an important point for a second. Why am I talking about observation so much, and why am I emphasizing it so much? It's because it's not okay, it's because it's the first step. It's because it's the first step. We can't ignore the fact that our human minds filter out different things and that our perception plays a really important role of how we as humans find out what's there. So if we're trying to look for something, well, I personally am, if we're trying to look for something that might be considered invisible or that is not understandable, the first step to see it is, or to even get close to measuring it, is you have to notice it first. You have to notice it first. So I don't know if all this psychology stuff is like the be all end all of this, of the answer is metaphysical and it's the answer is experience and being, but I do know that it is the first step, because how do you find something that you don't know where it is or you don't know where to look? You have to first open up your peripheries. You have to open up your perception. You have to allow yourself, you have to attune yourself to be able to see something different. So it's the first step. All right, so now a few scattered thoughts here about, okay, now we're kind of getting into chaos theory a bit. Probably go another, I don't know, 15 minutes. Getting into chaos theory and rhythm, deviation, and all this stuff. So, still on our brains for a moment, though. These next few slides were inspired by just thoughts over the last few days. Uh, our brains, our brains don't scan for rhythm, though. They scan for deviations. So so back to the deviation stuff though. This is about deviations from the norm, right? And this slide was actually inspired by this exact thing that I'm describing. So, when you think that you hear something and you look outside, and it's so funny because this is such a subtle psychological thing, I think. When you think that you hear something, and so then you look to the region that you think that you heard something, and so you're scanning, right? You're looking. But what are you really looking for? Well, it depends on where you're looking. And this happened to me like 2 days ago. This is why I had the thought. And so I thought that I like saw a person or saw something in the backyard, and I looked, and then you keep your eyes there for a little bit. And what are you scanning for though? You're scanning for a deviation from the norm, but your mind would accept random noise, probably. Your mind would accept the trees rustling. Your mind would also accept a rhythm, but your mind wouldn't accept like a chaotic deviation, like a deviation from the norm, but that felt like a certain pattern for us. And so that unexpected behavior, it signals agency, meaning sentience in a way. I mean, right? Because then what does that say? So when you see that deviation from the norm, then you say, "Oh my God, there's someone in my backyard." Intruder alert. Um, right? So it's signaling though like a life force, like a agency, like life, consciousness, I think. And so that's kind of, to me, that was like an interesting bridge between the psychology of those deviate, like the patterns, and I don't know, deviating from the norm. All right, then another cool thought I had was about, this is kind of a similar idea about the patterns and stuff, was why does a flame feel alive, right? What is it about the pattern and the motion of a flame that feels alive to us? And this is sort of about like the consciousness agency thing. And it's our brains, they're recognizing the combination of its pattern with unpredictability in it. And so it's so fascinating because it gets into this whole thing of how, okay, this spectrum of like pattern versus randomness, and where consciousness and where life actually lives in the middle. So what lives in the middle? Chaos, creativity, like humanness, consciousness, agency lives in the middle. And so then I thought this was like a cool visual, because too much noise, or sorry, too much synchronization, right? Too much rhythm. That is mechanical and boring. So this is kind of putting the spectrum. There's the rhythm is mechanical and boring. The noise doesn't really have any meaning, right? When you put it randomness, so what's the difference between chaos and randomness? Randomness doesn't really mean anything. Synchronicity, or when something's in sync, then that's the other end of the spectrum. But then chaos and agency and the things that clearly our universe, the patterns that our universe show us live in the middle. They live in this, oh, that's so cool. Yeah, that's so cool. They live in the middle. They live in this like chaotic, alive state. Everything that describes our universe, right? It's this cool sweet spot of interestingness. That's what I'll say. Interestingness. So all right. So, and that is another sort of form of a deviation from the pattern. So this is all kind of accumulating this is all accumulating to reality revealing itself, or more hints of the true nature of time and reality, and thing. What can we learn from these deviations from the pattern? What can we learn? So, all right, let's talk about chaos theory, which was some of the pinnacle of this whole thing. So, chaos theory, the definition of chaos theory is a chaotic system. So, a chaotic system, its most simple definition is that it's a system that it follows deterministic, meaning predictable. It follows deterministic, predictable rules, but the long-term behavior becomes unpredictable. But its long-term behavior becomes unpredictable, which really is a product of tiny fluctuations. So systems that are very sensitive to their initial conditions. And all that chaos theory, what I think is the most interesting part of chaos theory, what it really boils down to is um, as errors propagating, errors magnifying, a tiny little difference magnifying into something really big. And that's why we say it becomes impossible to predict. Or if you were to just make it a clean example of two separate systems. So to do a clean example, two separate systems, one starts off with a little tiny difference than the other one. We can't propagate that and track it and say, oh, that's totally fine. This one ends off here and this one ends off with a tiny little difference. That's not how it works. That tiny little difference doesn't translate to a tiny difference at the end. The tiny difference at the beginning translates to a huge difference at the end, because those tiny differences get amplified and amplified and amplified, and that's how they become a big difference. That's the gist of chaos theory and chaotic systems. The interesting thing, and like, this isn't a lecture on chaos theory, this is me sharing things and telling you what I find most interesting about them. What's interesting about this to me is that chaos theory was really one of the first things that was able to say, to look at things that were seemingly random, like this, like something, this is two pendulums going around. So we would look at something seemingly random and say, this whole thing is a mess. But there's actually order in it because it's built out of predictable systems. So that's kind of the beauty of chaos theory. It's able to look at something that is a mess and say, no, 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 that's actually not a mess. There is some structure in it. And but how would we have known there is structure in it? Maybe we didn't always. Um, so then what I think, yeah, this is what I think is, I would say, the coolest thing. Yeah, unpredictable. It really means it means yeah, it means too hard. It pretty much means too hard to measure. Or, okay, well, actually, here I actually realize I have a thing about predictability on this slide too. Chaotic systems it's like the weather. They're predictable short term. It's the long term, they're unpredictable. And it's because, but I think about this too, David, because I know I also am thinking about, like, well, and I guess I didn't get too detail. I didn't get this deep in my research enough for this class. But then I think of, like, well, what if you just follow the algorithm and keep following it and keep following the algorithm? Like, that's how my science mind works too. I think that maybe sometimes if they keep following, it depends on the type of system. They might be able to eventually predict, but the core idea is that is that a tiny change grows and grows and grows and grows, which creates which creates these long-term um unpredictability. And so I saw that, and then I was like, so when I realized that's really the core of chaos theory, I was like, that's so cool because it reminded me of the agency and the kind of the consciousness aspect of it. It's a small uncertainty or a small deviation taking on a life of its own in a way, right? It's saying you can't control me. That's so cool. All right. So the strange attractor. Um, Oh, yeah, yeah, yeah. Does this have to do with our ability to track distant planets and stars with incredible accuracy, but we still can't know for sure if it'll rain tomorrow? That's exactly what it is. That's exactly what it is. But even planetary systems are just like the whole Earth Moon thing, and there's a little bit of there is statistical variation in those too. But yeah, that's exactly what it is. The weather is the this conditions that kind of that propagate in the weather systems are what make it difficult to predict because we don't know how this one little temperature fluctuation is going to change that. And then another thing of chaos theory and everything is like your result the reason it gets propagated, oh, this is cool, the reason everything gets propagated is because it's like put a number into one equation, you get out some number, and then that output gets the input to the next thing. So, oh, it's kind of like a game of telephone in a way. It's kind of like telephone, like how the message gets blurry by the end. It's like through every single interaction, something changes. This is called the strange attractor, and this is an example of order hiding inside of chaos. So it's 8 o'clock. I'll probably have another 5 or 10 minutes of talking on here, just as an FYI for anyone here in the replay. And so, all right, this whole strange attractor thing, this was really cool. I had seen pictures of this, and like I told you, a lot of this stuff I only really researched for right now, and that's part of the reason that I did this. Helps me organize my own thoughts and curiosities. So this is this is a this is how a chaotic system propagates within reason. The takeaway of this whole thing of the strange attractor is that it's an unpredictable system technically, that is repeating its instructions, it's repeating its behavior, but it's staying within this bound shape. That's what the whole thing of the strange attractor is. That's the thing that's interesting, that's meant to be interesting about it, is it's both contained and has a structure, and it's following this whole thing, right? That's a level of containment. This shape is not going every which way. That's a level of containment, but it's a chaotic system, technically still. So one of the coolest things that I learned too close to when this class started to research in more detail is this whole thing of it kept on describing the strange attractor as, and the way that chaotic systems propagate, as a a never-ending stretching and folding, repeating. And I was like, it made me think of so many things regarding space-time. I was like, stretching and folding, stretching and folding. And that's how these systems create fractal behavior. It's the repetition of this process that creates this fractal branching. So then I've had all these visuals of kind of space-time like opening up and unfolding like an accordion, or sort of breathing some air into creating like a phase transition or a transformation of space-time. So now I have all these thoughts about stretching and folding and what does that mean for space-time, and that's just where my brain is right now, but I will have to look into that later. But stretching and folding, what does that all mean? So then, all right, just getting into the fractals and kind of wrapping up here. So the whole thing about what I find interesting about chaos theory, well, for one, it's revealing that there can be secret order in what looks like randomness or what looks like wild chaos, and there's a very big overlap between chaos and fractal behavior. And the ideas that I'm working with have to do with applying fractal behavior to space-time itself, to the fabric of space-time and existence itself. So where's the overlap? It's really that chaos is sort of the motion, and fractal behavior or fractals are the imprints or the footprints that are kind of left behind. They're like the shape, the echoes, the footprints, the imprints that are left behind from these chaotic processes. So, in more specifically, they're born. Fractals are born from simple rules repeating indefinitely. Simple rules repeating indefinitely, and then also another side note: fractals are the shape of the shape of energy dissipation. So, just in terms of other isolated systems, that's why lightning is fractal because it's energy dissipating. Rivers, and then also there's geological surface features. My friend at UCF studies fractal features on Mars, geological fractals on Mars, and the reason that the features are created is because it's kind of these gas bubbles like emerging, and they are dissipating energy into the material. So that fractal dendritic branching shape, it's the shape of energy dissipation, which I think is very significant. And I think that is reason enough to think that there's fractal behavior somewhere in space-time that we haven't observed yet. I think that's reason enough. It's the shape of energy dissipation. Where else is fractal behavior in nature that we just haven't found yet? That's kind of what I'm saying. So chaos creates fractal behavior, this echo left behind. And chaos theory supports that messiness, right? Messiness can be structure. Messiness can be structure, and absence of observation does not mean that something doesn't exist. Because before we understood these more chaotic patterns, right, or just looking at just zooming into that chaotic pattern or what we might perceive as some unpredictability, it doesn't mean that there's not a deeper structure. It doesn't mean that there's not some echoes left behind. So really what this now this is kind of just branching into my own ideas. And I mean, hey, we're really ending with questions, right? All of this, I don't have anything figured out. I have ideas and I have questions, and that's what I'm here for. So the question that it makes me think about, it makes me think about, okay, these deviations, we're trying to keep this solid, consistent time. Everything is deviating from the norm. There's these chaotic systems. Things aren't predictable, and if space-time itself, or if there were other traces of chaotic behavior, or some kind of dynamics, or like a deeper substructure of the universe that exhibited chaotic behavior. The question I'm posing is, what kind of structures could emerge from this sort of all of these chaotic structures, these repeated structures that maybe produce fractal behavior that create this branching? And really, what kind of signatures would it leave behind? So if there was some other chaotic substructure to space-time, what could it have emerging? And what could it reveal to us? And what signatures could it create space-time to branch, to fold, to repeat? That's kind of the coolest part, the repetition. Because I don't know, I guess I have thought about this. The repetition is the coolest part. Because if things repeat, that means that if there's repetition naturally built into, and fractal behavior naturally built into our universe and existence itself, you know what that means, right? We're one part of a larger repeated process. That's what that means to me. uh, that's what I would say. If that were to be closer to the truer nature of reality, that this repetition, right? Everything like repeats. If we could apply that to cosmology somehow, or to the fabric of space-time, the fabric of time, would it mean that we're one repeated expression? That's where my ideas are right now. So instability and chaotic behavior creates fractals when simple rules are repeated over and over again. And so, kind of to the philosophical, or a little bit more of the metaphysical perception part of it, back to the forcing of it all. I have this line in here: when you allow it to be chaotic, you can observe it and understand it. So, back to kind of being one with nature. That sounds whatever. It sounds exactly how it sounds, because we should be one with nature. When you can, you know, when you can stop forcing the processes of the universe or nature or anything that we're trying to understand. You can stop forcing it into your structure or stop forcing it into what you expect it to be. You allow it to be chaotic, open up your mind to observing it. Maybe it will reveal itself to you. So, other updated things, I like to sometimes update my previous thoughts into my new perspective. So, in my last master class, I was saying I was kind of using this terminology of extreme conditions, uh, inspired by extreme conditions, maybe have the ability to poke open space-time itself, like right, black holes, wormholes. First few minutes, like right after the Big Bang, inspired by extreme conditions, open up space-time. That's like my logic. I was thinking that extreme conditions perturb space-time, create some instability that leads to fractal behavior. But now I'm kind of questioning the term extreme because what do I mean by extreme condition? Who is it extreme to? We're calling it extreme. The word extreme is relative. It's extreme to us. But what if it's just a condition? What if calling it an extreme condition emphasizes the fact that it's hard to find? Emphasizes the fact that it's hard to exist when it actually can just exist because it's capable of existing and maybe it's just already there. All right. So then in terms of this is my last slide. So in terms of the literature and where do we look? You know, where am I researching and where have all these thoughts led me? Where I'm looking at is and the literature gap that I'm pointing to is empty space itself, quantum vacuum fluctuations and chaotic vacuum fluctuations, because this is empty space. This is saying we quantum field theory says that empty space is not empty, it's just the lowest energy state of the quantum field. So there's also these fluctuations. We don't know the true fundamental nature of space-time itself. That's an open question in science. And it's one of the biggest open questions that there is for sure. And so that's kind of the literature gap. We know that there's these fluctuations. So my question, where my current thoughts are, is where could the empty space or where could these quantum vacuum fluctuations, how could we take that thought and maybe see how that could apply to chaotic behavior or see if there's some other region in space that contains more. And you know, it's like I keep on, or I don't know, it's like I want to say it's hidden, I want to say it's hiding from us, but the more I think about perception, the more I think about the back to the speck of glitter, the sparkle, right? It's not continuously visible, but the information, so this is a speck of glitter like floating, and then all of a sudden the orientation is just right enough such that you see it, and then it just goes back to being invisible. That information was always there, but the conditions weren't right for us to see it. So I don't know what else, you know, chaos theory is pointing to things hiding in structure, hiding in seeming randomness, structure hiding in nothing. So what else is hiding? How is our mental perception affected by all of it? You know, how are we currently being so limited by what we expect to see, by the scientific community being so weird all the time? Sorry, that was just a personal frustration. Being so close-minded all the time? Whoops, sorry, am I angry? You can tell. It's fine. All right. So that's kind of my conclusion here. I'm looking into the vacuum of space-time and that's kind of where I think maybe some of these interesting ideas live. All right. So that's all I got. And I hope that was fun and took you on a fun journey. I hope that it left you with interesting things to think about. That's what I hope. Um, and it was fun and challenging and exciting for me to put together. It forced me to put my ideas together, even though it was difficult and rewarding. The only way to figure out what you're thinking is to force yourself to figure out what you're thinking. All of my thoughts are always so scattered. So, you know, it's kind of nice to put it all together. All right. So thanks to everyone that was in here. Any other yeah, if there were any if there are any questions. Thanks guys, and thanks for everyone that's in here. Plenty of my students and fam, thanks. And Yeah, thank you. Yeah, and I'd love to hear feedback here or separately offline, wherever, for if you're watching now or in the replay. And all right, cool. I'm looking forward to hearing what it inspired. But thank you all for showing up and thank you for having an open mind. And I can't wait to see where all these thoughts go. Bye.
Mutti.